Imagine a vessel so swift that it could carry you to Alpha Centauri, our nearest stellar neighbour, in just over 4 years. Imagine crossing the void between galaxies, witnessing the birth of stars in real time, tracing the spiral arms of distant nebulae with your own eyes. Imagine standing at the edge of the observable universe itself, touching the boundaries of creation. This is the dream of light-speed travel, whispered through generations of human longing, painted across countless works of science fiction, promised by starship engines that hum with impossible energy. Yet the universe, in its ancient and immutable wisdom, has written a law so fundamental, so absolute, that it cannot be broken, bent, or bargained with. Tonight, we confront the dark reality of why we can never, will never travel at the speed of light. Not because our technology is insufficient, but because the very fabric of reality forbids it. In films and novels, starships leap to light speed with the press of a button. Hyperdrives engage, stars stretch into lines. The cosmos becomes a highway of infinite possibility. We have been raised on these visions, nurtured by the promise that one day, somehow, humanity will break free from the crawling pace of conventional rockets and claim our birthright among the stars. It is a beautiful dream, luminous and intoxicating. But it is also a lie, or rather, an impossibility so deeply woven into the mathematics of existence that to travel at light speed would require us to unravel the universe itself. What we will explore tonight is not merely a limitation of engineering or energy. It is something far stranger, far more profound, and perhaps more unsettling. We will journey through the revelations of Einstein, through concepts that twist our understanding of time, mass, and causality. We will discover why the faster you move, the heavier you become, why time itself slows for the traveller while the universe ages around them, why reaching light speed would demand infinite energy, transforming you not into a voyager, but into an impossibility, a mathematical contradiction wrapped in flesh and metal. If you are listening to this as you drift towards sleep, or perhaps in the quiet hours when the world has fallen still, I invite you to take a moment. In the comments below, share with us where you're watching from and what time it is in your corner of the world. It is a small gesture, but it connects us across distances, reminding us that while we cannot travel at light speed, our thoughts, our curiosity, our shared wonder can span the globe in an instant. Tonight's journey will take us through the barriers that stand between humanity and the cosmic speed limit. We will examine the infinite energy problem, the paradox that says the closer you approach light speed, the more energy you need, until at the threshold itself, you would require all the energy in the universe. We will explore time dilation, the eerie phenomenon where your clock slows while distant worlds age centuries in what feels like moments. We will peer into the photon's perspective, where time does not exist, and causality itself begins to fray. And we will confront what this means for our future among the stars, not as conquerors of light, but as patient travellers of slower, more humble paths. So settle in. Let your breathing slow. Allow your mind to drift into the deep physics of space-time, where the universe reveals its most closely guarded secrets. Tonight, we do not seek to escape reality, but to understand it, to find peace in the elegant, unbreakable laws that govern all things. The speed of light is not a challenge to overcome. It is a truth to comprehend, and in that comprehension lies a strange, profound beauty. Let us begin. Before we understand why we cannot reach the speed of light, we must first understand why we're so desperate to do so. the desire to travel at light speed is not merely a scientific ambition. It is a dream born from confronting the most terrifying truth about our universe. The distances between stars are so vast, so incomprehensibly enormous, that they mock our current capabilities and render our fastest achievements almost meaningless. To grasp the scale of interstellar distance, we must first understand what a light year truly represents. Light, the fastest thing in the universe, travels at approximately 186,000 miles per second. In a single second, light could circle the Earth's equator more than 7 times. In 1 year, light travels nearly 6 trillion miles. This distance, 1 light year, is the unit by which we measure the cosmos. And yet, even the nearest star to our Sun, Proxima Centauri, lies 24 light years away. This means that light itself, travelling at the ultimate cosmic speed limit, takes over 4 years to reach our closest stellar neighbour. Let us place this in perspective. If we could somehow shrink the Earth to the size of a grain of sand, our Sun would be a sphere the size of a small orange positioned about 50 feet away. On this scale, Proxima Centauri would be located more than 2,500 miles distant. The space between stars is not merely empty. It is an abyss so profound that distance itself becomes abstract, a mathematical concept divorced from human experience. Now consider our current capabilities. Voyager 1, launched in 1977, is the fastest and most distant human-made object in existence. After more than 4 decades of continuous travel through the void, after harnessing gravity assist from Jupiter and Saturn, after being flung outward with all the momentum we could provide, Voyager 1 travels at approximately 38,000 miles per hour. This seems extraordinary until we compare it to the speed of light. At light speed, we would be travelling at 670 million miles per hour. Voyager 1, humanity's fastest achievement, is moving at roughly 0.6% the speed of light. At its current velocity, Voyager 1 would require over 70,000 years to reach Proxima Centauri. 70,000 years. Longer than recorded human history. Longer than agriculture has existed. Longer than civilization itself. This is the cruel mathematics of interstellar travel. The universe has presented us with distances so immense that our most impressive technological achievements become almost comically inadequate. We are like ancient sailors attempting to cross the Pacific Ocean in a rowboat, watching the horizon recede with each stroke, knowing that the destination lies beyond not just the visible world, but beyond lifetimes, beyond generations, beyond the span of empires. Yet despite these impossible distances humanity dreams, we have always dreamed. And nowhere is this dream more vividly expressed than in the realm of science fiction, where writers and visionaries have given form to our deepest longing, to transcend the limitations of physics itself and travel among the stars as easily as we once crossed oceans. Science fiction has not merely entertained us, it has shaped our cultural understanding of what space travel should be. In Star Trek, the Starship Enterprise traverses the galaxy at warp speed, bending space itself to achieve velocities that make light speed seem pedestrian. Captain Picard orders engage, and within moments the ship leaps across light years, arriving at distant worlds in time for commercial breaks. In Star Wars, the Millennium Falcon activates its hyperdrive and vanishes into hyperspace, where the normal rules of physics are suspended and entire star systems flash past in streaks of light. These stories have become embedded in our collective imagination, creating an expectation that interstellar travel should be not just possible, but routine, even casual. This cultural obsession with faster-than-light travel reveals something profound about human nature. We are a species that refuses to accept impossible as a final answer. Throughout history, we've been told that certain barriers could never be broken, only to shatter them through ingenuity and determination. For millennia, humans believed that travelling faster than a horse could run was impossible, perhaps even fatal. Then came trains, automobiles, aircraft. We were told that breaking the sound barrier would destroy any vessel that attempted it, that the very air would become an impenetrable wall. Chuck Yeager proved otherwise in 1947, accelerating past Mach 1 and opening the door to supersonic flight. Each generation has pushed against the speed limits of their era. From horses capable of 30 miles per hour, we progressed to steam locomotives reaching 60 miles per hour, then to automobiles exceeding 100 miles per hour. The first powered aircraft flew at barely 30 miles per hour. Within decades, we were flying faster than sound. Within a century, we were launching rockets into space at 25,000 miles per hour, fast enough to escape Earth's gravitational embrace entirely. This progression has been exponential, each breakthrough building upon the last, creating a historical pattern that suggests unlimited acceleration, unlimited possibility. And so we ask, why should light speed be any different? If we have broken every previous barrier, overcome every limitation our ancestors considered absolute, why should this cosmic speed limit be the exception? The dream of light-speed travel is seductive precisely because it seems like the logical next step in humanity's conquest of velocity. We have gone from walking to flying, from flying to orbital velocity, from orbital velocity to interplanetary travel. Surely, the reasoning goes, light speed is simply the next barrier waiting to be broken. But the dream of light speed is motivated by more than historical optimism or science fiction fantasies. There are profound, practical reasons why humanity desperately needs faster-than-light travel, reasons that touch upon the very survival of our species. Earth, for all its beauty and abundance, is a fragile oasis in a hostile universe. It exists in a narrow zone around our sun where temperatures allow liquid water to exist. It is protected by a magnetic field that shields us from deadly radiation. It has an atmosphere that provides oxygen and filters harmful ultraviolet light. Yet this protection is not permanent. Our sun will eventually expand into a red giant, engulfing the inner planets and rendering Earth uninhabitable. Asteroid impacts, though rare, have caused mass extinctions in the past and will occur again. Climate change, resource depletion, pandemics, nuclear war. These are not distant hypothetical threats, but immediate challenges that could compromise our civilization or even our survival as a species. The ultimate answer to these existential risks is dispersion. If humanity remains confined to a single world, we remain vulnerable to any catastrophe that could befall that world. But if we could spread across multiple star systems, colonizing worlds light years apart, our species would become virtually extinction-proof. No single disaster could threaten all of humanity. We would become a truly spacefaring civilization, resilient and enduring. Light-speed travel would make this vision achievable within human lifetimes. At light speed, we could reach Proxima Centauri in just over 4 years. We could explore nearby star systems, identify habitable worlds, and establish colonies before the explorers who discovered them had even reached old age. Resources that are scarce on Earth, rare metals, water ice, energy from distant stars would become accessible. the entire galaxy, with its hundreds of billions of stars and potentially trillions of planets, would open before us like an infinite frontier. Without light-speed travel, interstellar colonization becomes a multi-generational endeavor, requiring generation ships, massive vessels where entire communities would live, reproduce, and die during journeys lasting centuries or millennia. The people who arrived at the destination would be the distant descendants of those who departed, separated by dozens of generations, speaking languages and holding values potentially unrecognizable to their ancestors. Such missions are theoretically possible, but they require a kind of civilizational commitment and stability that humanity has rarely demonstrated. Lightspeed travel would transform this slow, uncertain expansion into something rapid and purposeful. It would allow us to explore, to learn, to adapt, and to return with knowledge before technology and society had changed beyond recognition. It would make the stars not just destinations, but neighborhoods. It would turn the galaxy from an unreachable abstraction into a place where human history could unfold across thousands of worlds. This is why we want light speed. Not merely because it would be impressive, not simply because science fiction has taught us to expect it, but because the survival and flourishing of humanity may ultimately depend upon our ability to transcend the limitations of our birth world and spread among the stars. And yet, there is something deeper still driving this obsession, something primal and ancient that predates science fiction and space exploration. Humans are explorers by nature. This is not a metaphor or a poetic flourish. It is encoded in our DNA, written into the very structure of our brains. Our ancestors left the safety of Africa and dispersed across the entire globe, crossing oceans on fragile rafts, traversing frozen tundra, ascending mountains, and penetrating jungles. They did this not because it was easy or safe, but because the urge to see what lies beyond the horizon is fundamental to our species. We are the descendants of those who were curious, those who were restless, those who looked at an unknown landscape and felt compelled to explore it. The ones who stayed behind, who never ventured beyond familiar territory, they left fewer descendants. Evolution has favored the explorers, the risk-takers, the dreamers who believed that something better, something more, lay just beyond the edge of the known world. Space is simply the final frontier for this ancient drive. The stars are the ultimate horizon, and light speed is the vessel we imagine could carry us there. To abandon the dream of light-speed travel would be to deny something essential about human nature. It would be an admission that there are places we can see but never reach, destinations we can identify but never visit, questions we can ask but never answer. And so we dream. We dream of starships that can cross the light years in weeks instead of millennia. We dream of colonies on worlds orbiting distant suns. We dream of a future where humanity is not trapped on a single fragile world, waiting for the inevitable catastrophe, but dispersed among the stars, enduring and eternal. This dream is beautiful. It is inspiring. It speaks to the best aspects of human ambition and imagination. But the universe, as we are about to discover, does not care about our dreams. The laws of physics are not suggestions. They are absolute, unyielding, and far stranger than science fiction ever imagined. The speed of light is not simply a barrier waiting to be broken. It is woven into the fundamental structure of reality itself, and the reasons we cannot reach it are not merely technical challenges, but profound truths about time, energy, causality, and the very nature of existence. To understand why we cannot travel at light speed, we must journey into the realm of Einstein's relativity, where time bends, distances contract, and the universe reveals itself to be far more mysterious and unforgiving than we ever imagined. In the year 1905, a young patent clerk in Bern, Switzerland, sat at his desk contemplating a question that had haunted him since childhood. His name was Albert Einstein, and the question was deceptively simple. What would it be like to ride alongside a beam of light? This was not idle daydreaming. This was a thought experiment that would shatter centuries of scientific certainty and reveal a truth so profound, so unsettling, that it would reshape our understanding of reality itself. Einstein imagined himself travelling at the speed of light, holding a mirror in front of his face. Would he see his reflection? According to classical physics, if he were moving at the speed of light, the light from his face could never catch up to the mirror. The reflection would vanish. But light does not behave this way. Light always moves at light speed, regardless of the observer's motion. From this simple paradox emerged one of the most revolutionary papers ever written, on the electrodynamics of moving bodies. In it, Einstein proposed something radical. The speed of light is absolute. It is not relative to the observer's motion. It is constant, unchanging, eternal. Light always travels at exactly 299,792,458 meters per second in a vacuum, whether you're standing still, flying toward it, or racing away from it at unimaginable speeds. This revelation was not merely counterintuitive, it was heretical. For thousands of years, humanity had believed that space and time were fixed, absolute stages upon which events unfolded. If you threw a ball forward from a moving train, its speed would be the train's speed plus the speed of your throw. This was Galilean relativity, the physics of everyday experience, the physics that made sense. But Einstein's revelation demanded something different. If light speed never changes, then something else must. That something was space itself, and time itself. The constancy of light speed is the foundation upon which all of special relativity rests. Imagine two observers, one standing on a platform, another aboard a spacecraft, travelling at half the speed of light. A beam of light passes between them. Classical physics would suggest that the observer on the spacecraft should measure the light moving more slowly relative to their motion. But experiments, meticulously performed and endlessly repeated, show otherwise. Both observers measure the light travelling at exactly the same speed. Not approximately the same, exactly the same, down to the last meter per second. This is not an illusion. This is the structure of reality. Light does not adjust its speed to accommodate observers. Space and time adjust themselves. They stretch, compress, dilate, and contract to preserve light's constancy. The universe itself bends to uphold this cosmic speed limit. From this foundation, Einstein derived the most famous equation in physics, E equals m squared. Energy equals mass times the speed of light squared. This elegant formula reveals a startling truth. Mass and energy are not separate entities. They are two forms of the same thing. Mass is concentrated energy. Energy is liberated mass. And the conversion factor between them is the speed of light, squared, an almost incomprehensibly large number. What does this mean for acceleration? For the dream of reaching light speed? It means that as an object accelerates, as it gains speed, it also gains mass. Not in the sense that more atoms are added, but in the sense that its inertia increases. The faster you move, the heavier you become relative to the stationary universe. At ordinary speeds, this effect is negligible, invisible. But as you approach the speed of light, the effect becomes overwhelming. The closer you get to light speed, the more energy is required to accelerate further. Not just more energy, exponentially more energy. At 90% of light speed, your mass has roughly doubled. At 99%, it has multiplied sevenfold. At 99%, more than 20-fold. To reach exactly the speed of light would require infinite energy, not an enormous amount. Infinite. No matter how much energy you possess, it would never be enough. The universe imposes this limit not through force, but through structure. The speed of light is not a barrier we collide with. It is an asymptote we approach forever, never quite touching. The mathematical framework describing this phenomenon is called the Lorentz factor, named after Hendrik Lorentz, who derived the equations before Einstein interpreted their meaning. The Lorentz factor is expressed as gamma, a value that describes how time dilates, how lengths contract, and how masses increase as velocity approaches light speed. When you're stationary, gamma equals 1. Everything is normal. As your speed increases, gamma grows slowly at first, then rapidly, then catastrophically. At light speed, gamma becomes infinite. Time stops. Length contracts to 0. Mass becomes infinite. These are not metaphors. These are measurements, predictions that have been confirmed thousands of times in laboratories around the world. Particles in accelerators routinely reach 99% of light speed, and their behavior matches Einstein's predictions with astonishing precision. Their lifetimes extend, their masses increase, they resist further acceleration exactly as the Lorentz equations predict. Galilean relativity, the physics of everyday intuition, assumes that time flows the same for everyone, that space is uniform and unchanging, that velocities simply add together like numbers on a scale. This works beautifully at human speeds, but at relativistic speeds, speeds approaching light, intuition fails. Velocities no longer add simply. Time no longer flows uniformly. Space no longer measures the same. The universe reveals itself to be stranger, more interconnected, more profound than our ancestors could have imagined. Einstein's relativity replaces Galilean simplicity with a deeper, more accurate truth. Space and time are not separate. They are woven together into a single fabric called space-time. An event is not just a location in space or a moment in time. It is a point in space-time defined by 4 coordinates, 3 of space, 1 of time. Movement through space is inseparable from movement through time. The faster you move through space, the slower you move through time. The speed of light is the ultimate exchange rate between spatial motion and temporal motion. Light itself moves through space at maximum speed, and therefore does not move through time at all. For a photon, the journey from a distant star to your eye is instantaneous. No time passes. The photon is born and absorbed in the same timeless moment. This sounds like philosophy, but it is physics. We have proven it. In 1971, physicists Joseph Haffel and Richard Keating placed atomic clocks aboard commercial airplanes and flew them around the world, once eastward, once westward. When the clocks returned, they had measured less time than identical clocks left on the ground. Not by much, mere fractions of a microsecond, but exactly as Einstein's equations predicted. Time had dilated. The moving clocks had aged more slowly. Today, this effect is not a curiosity. It is a necessity. The Global Positioning System, GPS, relies on a network of satellites orbiting Earth at high speeds. These satellites experience time dilation. Their onboard clocks tick slightly faster than clocks on Earth's surface, due to both their velocity and the weaker gravitational field they orbit within. If engineers did not correct for relativistic effects, GPS coordinates would drift by miles within hours. Every time you use a navigation app, you are relying on Einstein's revelations from 1905. Special relativity is not abstract theory. It is woven into the technology of daily life. Particle accelerators provide even more dramatic proof. At CERN, the European Organization for Nuclear Research, protons are accelerated to 99. It's at 1% of the speed of light. At these speeds, the protons' masses increase by a factor of more than 7,000. They become thousands of times harder to accelerate. The energy required to push them even slightly faster grows exponentially. Engineers do not struggle against malfunctioning equipment. They struggle against the structure of space-time itself. The cosmic speed limit is not a suggestion. It is enforcement written into the laws of physics. Why does light itself travel at light speed? The answer lies in a unique property. Light has no mass. Photons, the particles of light, are massless. They do not resist acceleration. They do not accumulate inertia. From the instant they are created, they move at maximum speed. They have no choice. Massless particles must travel at the speed of light. They cannot travel slower. They cannot travel faster. They exist in a state of perpetual motion at the universe's absolute limit. Other massless particles behave the same way. Gluons, which bind quarks together inside protons and neutrons, also travel at light speed. Gravitons, if they exist, would do the same. Masslessness is not merely the absence of mass. It is a doorway to a different mode of existence, one where velocity is not variable but fixed, where time does not pass, where the journey and the arrival are one. The fabric of space-time itself is the stage upon which all of this unfolds. Space is not an empty container. Time is not an independent flow. They are dimensions of a unified structure, flexible and dynamic, shaped by mass and energy. When you move, you tilt your trajectory through space-time, exchanging motion through time for motion through space. The faster you move spatially, the slower you move temporally. Light speed is the boundary, the point where all motion is spatial and none is temporal. Einstein did not discover the cosmic speed limit by accident. He uncovered it through pure thought, guided by the principle that the laws of physics must be the same for all observers, regardless of their motion. From this principle, combined with the experimental fact that light speed is constant, all of special relativity follows inevitably, mathematically, beautifully. Time dilation, length contraction, mass increase, the equivalence of mass and energy, all of these are not separate phenomena. They are facets of a single truth. As we contemplate Einstein's revelation, we begin to see the universe not as a collection of objects moving through space and time, but as a tapestry of interwoven events, connected by the threads of causality, constrained by the geometry of space-time itself. The speed of light is not merely a speed. It is the conversion factor between space and time, the maximum rate at which cause can propagate to effect, the boundary between the possible and the impossible. This is the revelation that changed everything, not just our understanding of motion, but our understanding of reality. Space and time are not what they seem. Mass and energy are not separate. The universe is not built on solid certainties, but on relationships, on geometries, on limits that cannot be exceeded no matter how much we desire to exceed them. And so we arrive at the dark reality. The cosmic speed limit is not imposed by technology or fuel or engineering. It is imposed by the universe itself. To travel at light speed is not difficult. It is impossible, not improbable, not unlikely, but forbidden by the very structure of existence. Einstein did not build this barrier, he simply revealed it, and in doing so he showed us that the universe is far stranger, far more interconnected and far more beautiful than we ever imagined. We've dreamed of light speed. We've understood why it exists as a limit. Now we confront the first and most unforgiving barrier that stands between us and our cosmic aspirations. This is not a barrier of technology or time. It is a barrier woven into the fabric of reality itself, the infinite energy problem. As we accelerate toward the speed of light, the universe does not merely resist our progress. It demands an impossible price, a price that grows not linearly, but exponentially, until finally it becomes infinite. No amount of fuel, no matter how efficient, no source of power, no matter how vast, can overcome what mathematics reveals with cold clarity. To reach light speed is to demand infinite energy, and infinity by its very nature cannot be achieved. Let us begin with the equation that governs all motion in our universe. In classical physics, kinetic energy, the energy of motion, is calculated simply: 1/2 mass times velocity squared. At everyday speeds, this formula works perfectly. A car travelling twice as fast has 4 times the kinetic energy. A bullet moving 3 times faster requires 9 times the energy to accelerate. The relationship is predictable, manageable, comprehensible. But as we push toward relativistic speeds approaching a significant fraction of light, this comfortable equation begins to unravel. Einstein's special relativity introduces a correction factor, the Lorentz factor, represented by the Greek letter gamma. This factor accounts for how time, space, and energy transform as velocity increases. At low speeds, gamma is essentially 1. The relativistic effects are negligible, invisible, irrelevant to daily life. But as velocity climbs toward the speed of light, gamma does not increase gradually. It explodes. At 90% light speed, gamma is approximately 2.3. At 99% light speed, it reaches 7. At 99%, it soars past 22. And at 99% light speed, gamma exceeds 2000. This is not a gentle curve. It is a mathematical cliff, an asymptote that rises toward infinity, ensuring that the final fraction of light speed, that last infinitesimal increment, demands more energy than all the energy that came before it. The relativistic kinetic energy equation reveals this terrible truth with precision. Energy equals mass times the speed of light squared multiplied by gamma minus 1. As velocity approaches light speed, gamma approaches infinity. Therefore, kinetic energy approaches infinity. No matter how much energy we pour into acceleration, we can never quite reach that ultimate velocity. We can approach it asymptotically, endlessly, but never touch it. The universe has placed an invisible wall at exactly 299,792,458 meters per second. A wall not made of matter, but of mathematics itself. Consider what this means in practical terms. Let us imagine accelerating a single human being, an individual with a mass of approximately 70 kilograms, to various fractions of light speed. At 10% light speed, the energy required is roughly 3.2 times 10 to the 17th joules. This is equivalent to about 76 megatons of TNT, comparable to the largest nuclear weapon ever detonated. Already the energy cost is staggering. At 50% light speed, the energy requirement jumps to 2, 2 times 10 to the 18th joules, enough to power the entire United States for several days. At 90% light speed, we need 6, 3 times 10 to the 18th joules, more than the total annual energy consumption of humanity. And this is to accelerate just one person, not a spacecraft, not supplies, not life support systems, just the mass of a single human body. But the truly dark reality emerges when we push further. At 99% light speed, the energy required exceeds 4 times 10 to the 19th joules, equivalent to all the energy humanity produces in several years, concentrated into the acceleration of one individual. At 99%, we need more than 10 times 10 to the 19th joules. At 99%, the figure climbs beyond 7 times 10 to the 20th joules. The numbers cease to have human meaning. They become abstract symbols representing quantities of energy we have never harnessed, never witnessed, perhaps never could. To accelerate a human to 99% light speed would require energy equivalent to the total mass energy of several kilograms of matter, completely converted to pure energy according to E equals mc squared. And still, we would not have reached light speed. We would only have approached it, infinitesimally closer, but still separated by an unbridgeable gap. This is the asymptote problem, the cruel joke that the universe plays on our ambitions. Going from rest to 50% light speed requires a certain, albeit enormous, amount of energy. Going from 50% to 90% light speed requires approximately the same amount again, but going from 99% to 99% light speed requires more energy than going from 0% to 99%, and going from 99% to 99% requires even more. Each additional 9 we add after the decimal point doubles, triples, or quadruples the energy requirement. The final approach to light speed is not a hill to climb, but a vertical wall that extends upward forever. No matter how much energy we possess, there is always another decimal place, another fraction of a percent, another impossible increment demanding infinite power. The reason for this nightmare is deeply embedded in relativity itself. As an object accelerates, it does not merely move faster, it becomes heavier. Not in the sense of gaining more atoms or more substance, but in the sense of possessing greater inertia, greater resistance to further acceleration. This is relativistic mass increase. An object's mass, from the perspective of an outside observer, grows according to the same Lorentz factor that governs time dilation and energy. At rest, a proton has a rest mass of approximately 1/67 times 10 to the negative 27th kilograms. At 90% light speed, its effective mass more than doubles. At 99% light speed, it becomes more than 22 times heavier. At 99% light speed, its mass increases by a factor of thousands. The object has not changed. No particles have been added, yet it has become, in every measurable sense, thousands of times more massive. Accelerating it further requires pushing against this ever-increasing inertia, like trying to move a mountain that grows heavier with every step you take toward it. We do not need to theorize about this. We experience it every day in particle accelerators. The Large Hadron Collider, buried beneath the border of France and Switzerland, accelerates protons to 91% the speed of light. At this velocity, the protons are moving so close to light speed that they circle the 27-kilometer ring more than 11,000 times per second. Their relativistic mass has increased by a factor of over 7,000. A single proton, normally weighing almost nothing, now possesses the kinetic energy of a flying mosquito. This may sound trivial until you realize that a mosquito is trillions upon trillions of times more massive than a proton. The energy required to accelerate trillions of protons to this speed consumes enough electricity to power a small city. And even with all this power, the LHC cannot push protons to light speed. It can only approach it, closer and closer, spending exponentially more energy for each additional decimal place of precision. The universe will not allow the final step. Some have proposed antimatter as the solution, the ultimate fuel. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to Einstein's equation. No chemical reaction, no nuclear fission or fusion can match this efficiency. A single kilogram of antimatter combined with a kilogram of matter releases approximately 8 times 10 to the 17th joules, equivalent to 43 megatons of TNT. In theory, antimatter propulsion could provide the energy density necessary for relativistic travel. But even perfect fuel conversion cannot overcome the infinite energy barrier. To accelerate a modest spacecraft of 1,000 kilograms to 99%, light speed would require annihilating approximately 15,000 kilograms of matter and antimatter combined. To reach 99% light speed, we would need closer to 70,000 kilograms, and to approach even closer, the fuel requirements grow without bound. We would need more antimatter than the mass of the spacecraft itself many times over. The rocket equation, which governs all propulsion, becomes a death sentence at relativistic speeds. We cannot carry enough fuel to accelerate the fuel we need to carry. Even if we imagined an external energy source, a civilization capable of harnessing the entire output of a star, beaming energy to our spacecraft as it accelerates, we encounter the same wall. The energy required to push an object from 99% to 99. 9% light speed is greater than the energy needed to accelerate it from rest to 99. 9%, no matter how advanced the technology, no matter how abundant the energy, the mathematics does not bend. The asymptote does not flatten. Infinity remains infinite. This is the first barrier. The energy problem is not a challenge to overcome with better engineering. It is a fundamental law of nature. As velocity approaches light speed, energy requirements approach infinity. There is no workaround, no loophole, no clever trick that allows us to bypass this reality. The universe has spoken, and its message is absolute. Light speed is not merely difficult to reach, it is impossible for anything with mass. We can dream of travelling close to light speed, asymptotically approaching that ultimate velocity, but we can never touch it. The final increment remains forever out of reach, guarded not by technology or distance, but by the infinite energy demand woven into the structure of space-time itself. As we absorb this dark reality, we are forced to confront a deeper truth. The universe is not designed for our convenience. The laws of physics do not care about our ambitions, our curiosity, or our longing to explore the stars. They simply are. And in their indifference, they have placed a limit on how fast we can travel, how far we can go, how much of the cosmos we can ever hope to witness. The infinite energy problem is not a temporary obstacle. It is a permanent boundary, a horizon we can approach, but never cross. A reminder that even in our most advanced technologies, we remain bound by the same equations that govern falling apples at orbiting planets. The speed of light is not just a velocity, it is the edge of possibility itself. But there is something darker waiting in the equations of relativity, something that goes beyond energy and mass. It is the realization that if we could somehow reach the speed of light, we would not just be traveling through space. we would be travelling away from time itself. Time dilation is not a minor side effect of approaching light speed. It is a fundamental transformation of reality. At relativistic velocities, time itself slows down for the traveller, while the rest of the universe continues forward at its normal pace. This is not an illusion or a mathematical trick. It is a measured, proven phenomenon that strikes at the heart of what it means to exist in a shared moment with the rest of humanity. Imagine embarking on a journey to a distant star, travelling at 90% the speed of light. Your spacecraft accelerates, the engines burning with unimaginable power, and you begin to move through space at speeds that defy human comprehension. Inside your vessel, time feels normal. Your heartbeat is steady. Your watch ticks at its usual rhythm. You eat, sleep, and breathe as you always have. But outside, beyond the walls of your ship, time is racing forward. When you return to Earth after what feels like a journey of just a few years, you step out to discover that decades have passed. The people you knew are older, if they're still alive at all. The world has changed beyond recognition. Technologies you never imagined now dominate daily life. Buildings have risen and fallen. Entire generations have been born and have grown old while you are gone. You have not aged, but you have been exiled from your own time. This is the twin paradox, one of the most haunting consequences of special relativity. If one twin stays on Earth, while the other travels at near light speed and then returns, they will no longer be the same age. The travelling twin will have experienced less time, their cells will have divided fewer times, their memories will span fewer days. They will be younger, not by choice or technology, but by the inexorable mathematics of space-time itself. The reason for this is deeply embedded in the structure of reality. Time is not a fixed backdrop against which events unfold. It is dimension, interwoven with the 3 dimensions of space into a single fabric called space-time. Everything in the universe moves through space-time at a constant speed, the speed of light. But we can divide that motion between movement through space and movement through time. When you sit still, you're moving through time at maximum speed. Every second you age by 1 second. But when you begin to move through space, some of your motion through time is redirected into motion through space. The faster you move through space, the slower you move through time. At everyday speeds, this effect is imperceptible. But as you approach the speed of light, time dilation becomes dramatic, unavoidable, and absolute. At 90% the speed of light, time slows by a factor of about 2, 3. For every year that passes on your spacecraft, 3 years pass on Earth. At 99% light speed, the factor becomes 7. 1 year for you equals 7 years for everyone else. And at 99% the speed of light, time dilation reaches a factor of over 200. A single year of your subjective time corresponds to 2 centuries passing in the universe you left behind. These are not hypothetical numbers, they are predictions of Einstein's equations confirmed by countless experiments. We have watched them unfold in laboratories, in particle accelerators, and in the cosmos itself. Consider the muon, a subatomic particle created when cosmic rays collide with molecules in Earth's upper atmosphere. Muons are unstable. They decay rapidly, with a half-life of just 2 microseconds. At the speed they travel, even moving at nearly the speed of light, they should decay long before reaching the ground. Simple calculations show that most muons created at an altitude of 10 kilometers should not survive the journey to Earth's surface, and yet they do. In vast numbers, muons reach the ground and are detected by instruments worldwide. How is this possible? The answer is time dilation. From the muon's perspective, time is moving more slowly. Its 2.2 microsecond lifespan, measured in its own reference frame, stretches into a much longer period when observed from Earth's frame of reference. The muon experiences its brief existence, but to us, it appears to live long enough to complete its journey. Time itself has bent to accommodate the mathematics of relativity. This is not theory, this is measurement. Muons reaching Earth's surface are direct physical proof that time dilation is real. Atomic clocks provide another undeniable confirmation. In 1971, physicists Joseph Haefel and Richard Keating placed atomic clocks on commercial airliners and flew them around the world, once eastward and once westward. When the clocks were compared to identical clocks that remained on the ground, they showed measurable differences. The clocks that travelled through space at high speeds had aged less than their stationary counterparts. The differences were tiny, mere nanoseconds, but they matched Einstein's predictions with astonishing precision. Today, this effect is not just an experiment, it is a necessity. The Global Positioning System, GPS, which guides billions of devices across the planet, must account for time dilation to function accurately. The satellites orbiting Earth are moving at high speeds relative to the surface, and they are also experiencing weaker gravitational fields. Both effects influence the rate at which time passes for the satellite clocks compared to clocks on Earth. If these relativistic corrections were not applied, GPS coordinates would drift by several kilometers each day. Navigation systems would fail. The entire infrastructure of modern positioning would collapse. Time dilation is not abstract philosophy. It is woven into the technology we use every day, but the implications go deeper, far beyond muons and satellites. Time dilation brings with it the breakdown of simultaneity, the concept that two events can happen at the same time. In our everyday experience, simultaneity seems obvious. If two fireworks explode at the same instant, we assume they exploded simultaneously for everyone, everywhere. But in the universe revealed by relativity, this assumption is false. Whether two events occur simultaneously depends entirely on your state of motion. Observers in different reference frames, moving at different velocities, will disagree about the order in which events happen. One observer might see event A occur before event B, while another observer moving at a different speed might see event B occur before event A. A third observer might see them happen at the exact same moment. There is no absolute now. The present moment is not a universal slice through time that everyone shares. Instead, each observer carries their own present with them, shaped by their velocity through space-time. The faster you move, the more your perception of simultaneity diverges from others. This is not a matter of perception or signal delay. It is not that light takes time to reach you, creating the illusion of different timings. The events themselves occur in different orders for different observers. The universe does not have a single agreed-upon timeline. It has countless overlapping timelines, each equally valid, all coexisting within the framework of space-time. As you approach the speed of light, this effect becomes extreme. Events that seem simultaneous to someone at rest are stretched across vast intervals of time in your reference frame. The concept of right now loses all meaning. You're no longer synchronized with the rest of humanity. You are drifting through a different layer of time, watching the universe unfold at a pace dictated by your velocity. Accompanying time dilation is another strange phenomenon, length contraction. As you accelerate toward light speed, distances in the direction of your motion shrink. A journey that would take light years to complete at rest appears shorter when you are moving at relativistic speeds at 99. 19% the speed of light, a distance of 100 light-years contracts to less than half a light-year in your reference frame. This is not an optical illusion. Space itself is compressed along the axis of motion. The universe, from your perspective, becomes flattened. Stars that were separated by vast gulfs of emptiness suddenly appear closer together. You could cross interstellar distances in what feels like months or years, even though centuries are passing for everyone else. But here lies the horror. You can travel to distant stars. You can see alien worlds and distant nebulae. You can witness sights no human has ever seen. But you can never come home, not to the home you left. Every second you spend travelling at light speed pushes you further from the timeline of Earth. The people you loved, the culture you knew, the era you belonged to, all of it slips away, aging into dust while you remain frozen in your own pocket of time. This is the philosophical nightmare embedded in the equations of relativity. You become unstuck in time, a wanderer through epochs, unmoored from the shared experience of humanity. The stars may be within reach, but connection, belonging, and the passage of a shared history are lost forever. You would return not as an explorer, but as a ghost from the past, visiting a future that has moved on without you. The mathematics are elegant but merciless. The Lorentz factor, often written as gamma, quantifies time dilation. It is calculated as 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. At low speeds, gamma is nearly equal to 1, meaning time passes normally. But as velocity approaches the speed of light, gamma grows without bound, stretching time dilation toward infinity. At 90% light speed, gamma equals approximately 2.29. At 99% light speed, gamma reaches 7.9. At 99% light speed, it becomes 22.4, and at 9% light speed, gamma climbs to over 223. For every year you experience travelling at this speed, more than 2 centuries pass in the outside universe. These numbers are not theoretical fantasies. They are the foundation of particle physics. Every experiment in a particle accelerator confirms them. Subatomic particles racing through colliders live far longer than they should, their decay rates slowed by time dilation. Physicists depend on these equations to predict the behavior of particles moving at near light speeds. Without understanding time dilation, modern physics would be impossible. And yet, even though time dilation is proven, measured, and applied daily, it remains deeply unsettling. It means that the universe does not operate according to our intuitions. Time is not universal. Simultaneity is not absolute, and anyone who travels at relativistic speeds is no longer participating in the same flow of time as the rest of humanity. We are bound by the ticking of a shared clock, invisible but undeniable, woven into the structure of space-time itself. To break free from Earth's timeline is to sever the bond that connects us all, to drift alone through a universe where past, present, and future blur into a single, incomprehensible continuum. This is the second barrier to light-speed travel. Not just energy, but time itself. The universe allows us to approach the speed of light, but at a cost we cannot ignore. We trade our place in history for velocity. We exchange the companionship of our species for the cold mathematics of space-time. And as we push closer to that ultimate speed, we discover that the real darkness is not the void between stars. It is the unbridgeable chasm that opens between the traveller and everyone left behind. Time, once thought to be the steady heartbeat of existence, becomes a prison, isolating those who move too fast from the only home they have ever known. This is why we cannot travel at the speed of light, not because the universe forbids it, but because in crossing that threshold, we would lose the very thing that makes the journey meaningful, the ability to return and share what we have seen. We journey now into the strangest territory of all, a realm where time ceases to exist and distance collapses into nothingness. Here, at the edge of light speed, we encounter not just physical barriers, but philosophical ones. The universe is not merely preventing us from travelling at light speed. It is protecting the very fabric of cause and effect, the fundamental logic that allows existence itself to make sense. This is the third barrier, the most profound and unsettling of all, the perspective of light itself and the preservation of causality. Imagine for a moment that you could achieve the impossible, that you somehow became a photon, a particle of light, racing through the cosmos at 186,000 miles per second. What would you experience? The answer is more bewildering than anything science fiction has ever conceived. From the photon's perspective, time stops completely, not slows, not approaches zero, stops, absolutely and eternally. A photon emitted from the surface of a distant star billions of light years away experiences no passage of time during its journey to Earth. From its point of view, the moment of its birth and the moment of its absorption into your eye are the same moment. There is no journey, there is no duration. The photon exists in an eternal now, a frozen instant that spans the entire universe. To travel at light speed is to step outside of time itself, to become something that does not age, does not change, does not experience the flow of moments that defines existence for everything else in the cosmos. But it is not just time that vanishes. Distance, too, collapses to zero. From the photon's frame of reference, the universe contracts along the direction of travel until all space becomes a single point. The star it left and the planet it reaches are not separated by billions of miles. They are occupying the same location. The photon traverses the entire universe instantaneously, because from its perspective, there is no universe to traverse. All of space and all of time compress into a dimensionless singularity of experience. This is not science fiction. This is the mathematical reality of special relativity taken to its logical extreme, and it reveals something profound. Light speed is not a speed you can reach. It is a boundary between existence and non-existence, between time and timelessness, between the universe as we know it and something utterly alien. To travel at light speed would be to cease experiencing reality altogether. You would not arrive at your destination. You would never have left. The journey and the arrival would be indistinguishable, merged into a single impossible moment. This strange perspective of the photon leads us to an even darker realization. If we could somehow exceed the speed of light, we would not simply be moving very fast. We would be shattering causality itself. We would be enabling time travel into the past, and with it, unleashing paradoxes that would tear the logical structure of the universe apart. Consider this carefully. In relativity, simultaneity is not absolute. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different velocity. This is not an illusion. It is a fundamental property of space-time. Now imagine a spacecraft that could travel faster than light. From one observer's perspective, the ship departs Earth and arrives at a distant star. But from another observer's perspective, moving at a different velocity relative to the ship. The ship arrives at the star before it left Earth. The effect precedes the cause. Time flows backward. This is not a minor inconvenience. It is a catastrophic violation of causality, the principle that causes must precede effects. Without causality, the universe becomes a chaotic nonsense where events have no logical order, where outcomes can influence their own beginnings, where the future reaches back to alter the past. The universe we inhabit, where actions have consequences and effects follow causes, depends absolutely on the existence of a cosmic speed limit. Light speed is not just a barrier to travel, it is the guardian of logic itself. Physicists have speculated about hypothetical particles called tachyons, particles that always travel faster than light, just as ordinary particles always travel slower than light. If tachyons existed, they would inhabit a bizarre realm of reverse causality. Their behavior would violate our intuitive understanding of time. A tachyon would appear to exist before it was created, traveling backward through time from an observer's perspective. It would lose energy as it accelerated, gaining energy as it slowed down, the opposite of normal matter. More troubling still, tachyons could be used to construct closed causal loops, situations where an effect could be its own cause, where messages could be sent into the past to prevent their own transmission. These are not merely philosophical puzzles. They represent genuine logical contradictions. The grandfather paradox, the classic time travel conundrum where you travel to the past and prevent your own birth, becomes physically possible in a universe where faster-than-light travel exists. The universe would be forced to resolve contradictions that have no resolution. Existence itself would become incoherent. This is why most physicists believe tachyons do not and cannot exist. The universe forbids them not because they are difficult to create, but because their existence would make the universe itself impossible. The structure of causality is elegantly captured in what physicists call a light cone. Imagine a point in space-time representing here and now. From that point, light expands outward in all directions at 186,000 miles per second, creating an expanding sphere. If we draw this on a diagram with time as the vertical axis and space as the horizontal axis, the path of light forms a cone shape. The interior of this cone, the region within the light speed boundary, represents all the events that can be causally connected to the present moment. Everything in your past light cone represents events that could have influenced you. The light from those events has had time to reach you. Everything in your future light cone represents events you could potentially influence. Your light, your actions, your information could reach those events. But everything outside the light cone, the region separated from you by more space than light could cross in the available time, is causally disconnected from you. Those events can neither affect you nor be affected by you. They exist in a kind of cosmic elsewhere, beyond the reach of cause and effect. This structure is not arbitrary. It is the logical skeleton of the universe. The light cone defines what is possible and what is not, what can influence what, which events can be connected and which must remain separate. Faster-than-light travel would allow you to leap outside your light cone, to reach events that should be causally forbidden to you. In doing so, you would create pathways for information to flow backward in time, closing causal loops and generating paradoxes. The universe enforces the light speed limit not out of spite, but out of logical necessity. Without it, the past, present, and future would collapse into an undifferentiated chaos. Information, it turns out, is the key to understanding this barrier. What we call the speed of light is more accurately described as the speed of information, the maximum rate at which any signal, any message, any influence can propagate through the universe. Nothing, no particle, no wave, no field, no whisper of energy or force can carry information faster than light. This is not a technological limitation. It is a fundamental property of space-time itself. If information could travel faster than light, cause and effect would become untethered. You could send a message to yourself in the past, warning yourself not to send the message. You could receive information about the outcome of an event before the event occurred, then use that information to change the outcome, creating a logical impossibility. The universe preserves causality by imposing an absolute speed limit on information. Light speed is the speed at which reality itself updates, the rate at which one region of the universe can communicate with another. This raises a tantalizing question. Are there loopholes, ways to circumvent the light speed barrier without actually exceeding it? One of the most famous proposals is the Alcubierre drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994. The idea is both elegant and audacious. Instead of moving through space at faster than light speeds, you warp space-time itself, contracting space in front of your spacecraft and expanding space behind it, creating a bubble that carries you along at effectively faster than light, speeds relative to distant observers. The beauty of the Alcubierre drive is that it respects Einstein's speed limit locally. Inside the warp bubble, space-time is flat, and you're not moving faster than light relative to the space immediately around you. The bubble itself, however, surfs across the universe, carrying you faster than light without violating relativity. It is the ultimate cosmic shortcut, a way to cross vast distances in compressed time without technically breaking the rules. But before we celebrate this loophole, we must confront its staggering requirements. Creating an Alcubierre warp bubble would require exotic matter with a negative mass-energy density, something that may not exist in nature. The energy requirements are equally absurd, potentially requiring more energy than exists in multiple galaxies. Moreover, the very creation and control of such a warp bubble faces causality problems of its own. Some calculations suggest that information about the destination would need to travel faster than light to set up the warp field, reintroducing the same paradoxes we were trying to avoid. The Alcubierre drive remains a beautiful mathematical construct, a reminder that general relativity contains strange possibilities, but it also illustrates a deeper truth. Even our most creative attempts to circumvent the light speed barrier must ultimately respect causality. The universe allows warping, bending, and folding of space-time, but it does not allow violations of cause and effect. Locally, within any small region, light speed remains absolute. The cosmic speed limit is woven so deeply into the structure of reality that even exotic solutions to Einstein's equations cannot escape it. Why must the universe have a speed limit? Why is this barrier so fundamental that it cannot be breached even in theory without generating paradoxes? The answer lies in the nature of space-time itself. Einstein's great insight was that space and time are not separate entities, but aspects of a unified whole, space-time, a fabric in which every event has both a location and a moment. The speed of light is the conversion factor between space and time, the exchange rate that allows these two dimensions to interweave. Without a maximum speed, space-time would not have a unified structure. There would be no way to relate distances to durations, no framework for cause and effect, no coherent way for the universe to evolve from moment to moment. the speed limit is not imposed on the universe from outside. It emerges from within, from the very mathematics that describe how space and time are connected. Physics itself, this set of rules governing energy, matter and force, depends on this structure. Remove the speed limit and physics dissolves into incoherence. As we contemplate this third barrier, we are forced to acknowledge something humbling and profound. The universe is not keeping light speed from us out of cruelty. It is not hiding distant stars and galaxies behind an arbitrary wall. The cosmic speed limit exists because reality itself requires it. Causality, the logical flow of time, the relationship between cause and effect, these are not optional features of existence. They are the foundation upon which everything else rests. To travel at light speed would be to leave time behind entirely. To exceed it would be to shatter causality and plunge the universe into paradox. The photon's perspective, that strange, timeless view from the edge of possibility, shows us what lies beyond the boundary. Not freedom, not infinite speed, but the dissolution of experience itself. We are beings of time, creatures who exist within causality's flow. Light speed is not our prison. It is the structure that allows us to exist at all. We have journeyed through the mathematics of impossibility, through the warping of time and the infinite hunger for energy. We have stood at the threshold where mass becomes meaningless and causality itself begins to fracture. Now we must ask the question that defines our species' future. If we cannot reach the speed of light, what does this mean for humanity's place among the stars? The answer is not simple, it is not comforting, but it is not without hope. The speed of light is not merely a barrier, it is a fundamental rule written into the fabric of reality itself. We cannot break it any more than we can make 2 + 2 = 5. And yet, knowing this limit does not end our story. It transforms it. The question is no longer how do we break the rules, but rather how do we flourish within them. For centuries, humanity has dreamed of spreading across the galaxy, of visiting distant worlds in a single lifetime, of building an empire among the stars. Science fiction painted visions of warp drives and hyperspace, of ships that could leap across light years in moments. These dreams are beautiful, they are inspiring, but they are built on physics that does not exist. The universe we inhabit operates by different rules, rules that are more subtle, more elegant, and infinitely more constraining than our imaginations hoped. If we're to travel between stars, we must accept that the journey will be measured not in years, but in generations. The concept of a generation ship is both practical and profound. Imagine a vessel so large it contains entire ecosystems, forests and rivers, communities and cultures. Inside this travelling world, thousands of people live their entire lives, knowing they will never see the destination. They are born in transit. They raise children in transit. They grow old and die in transit, passing the mission forward like a torch carried through an endless night. Their great-great-grandchildren, people they will never meet, will be the ones to finally arrive at a distant star, to step onto alien soil, to see the light of a new sun. This is not the romantic vision of space exploration we were promised. It is something far more human. It is a testament to patience, to faith in the future, to the willingness to sacrifice individual dreams for the survival and expansion of our species. A generation ship is a society that exists solely to bridge the gap between worlds, a floating civilization whose purpose is not to arrive, but to endure. Yet even generation ships face profound challenges. How do we maintain social cohesion across centuries? How do we prevent genetic bottlenecks in a closed population? How do we ensure that technology remains functional across time spans that dwarf recorded human history? These are not engineering problems alone. They are questions about what it means to be human when home is neither where you came from nor where you are going, but the endless journey between. Another possibility emerges from the frontiers of biology and technology: suspended animation. If we cannot shorten the journey, perhaps we can shorten the experience of it. Imagine entering a chamber where biological processes slow to near stillness, where decades pass like a single night's sleep. The traveller closes their eyes in one century and opens them in another, the years consumed not by consciousness, but by dreaming darkness. This is not science fiction. Already, medical science has made remarkable advances in therapeutic hypothermia, in slowing metabolism, in preserving cellular function across extended periods. The leap from hours to decades is vast, but it is a leap of degree, not of kind. If we can solve the challenges of preventing cellular damage, of maintaining brain function, of reanimating the body without degradation, then suspended animation becomes not merely possible but practical. Yet here too the speed of light casts its shadow. Even if we sleep through the journey, even if subjective time collapses to nothing for the traveller, objective time still passes. The universe ages. The people we leave behind grow old and die. Civilizations rise and fall. We may close our eyes on a world we recognize and open them on one transformed beyond comprehension. Suspended animation solves the problem of human patience, but not the problem of cosmic distance. And then there is the most tantalizing possibility of all: time dilation, not as a barrier, but as a gift. At 99.9% of light speed, something extraordinary happens. The mathematics of special relativity, the same equations that make light speed impossible, suddenly become our ally. For the traveller aboard a spacecraft moving at such velocities, time slows dramatically relative to the stationary universe. A journey to a star 100 light-years away would take 100 years from Earth's perspective, but for those aboard the ship, subjective time might compress to mere months or even weeks. This is the strange mercy of Einstein's universe. The faster you travel, the less time you experience. At velocities approaching light speed, you could traverse the galaxy within a human lifetime, not because you broke the cosmic speed limit, but because you bent time itself around your journey. The trade-off is absolute and irreversible. While weeks pass for you, centuries pass for everyone you left behind. You return to a world that has aged beyond recognition. Your family, your friends, your entire civilization may be dust. You become a time traveller not by choice but by velocity, forever severed from the era of your birth. This is the dark poetry of near-light-speed travel. It offers freedom at the cost of connection. It grants us the stars, but asks us to sacrifice everything familiar in return. Yet humanity is not standing idle. Real projects, grounded in genuine physics, are already underway. Breakthrough Starshot, an initiative backed by some of the world's leading scientists and visionaries, proposes sending tiny spacecraft to the nearest star system, Alpha Centauri, using technology that exists today. The concept is elegant. Ultra-lightweight probes equipped with light sails, thin reflective surfaces pushed not by rockets but by powerful lasers fired from Earth. By focusing enormous laser arrays on these sails, we could accelerate the probes to 20% of light speed. fast enough to reach Alpha Centauri in approximately 20 years. This is not fantasy. This is engineering. The challenges are immense, the power requirements staggering, the precision needed almost incomprehensible, but the physics is sound. Within this century we may send emissaries to another star, tiny ambassadors carrying cameras and sensors, reporting back images of alien worlds 4 light-years away. 20% of light speed. Not the 100% we dreamed of, but enough. Enough to touch another star within a human lifetime. Enough to begin answering the oldest question our species has ever asked. Are we alone? Which brings us to one of the most haunting mysteries in all of science, the Fermi paradox. If the universe is so vast, if there are billions of stars, trillions of planets, countless opportunities for life to arise, then where is everyone? Why have we detected no signals, no visitors, no evidence of vast alien civilizations spanning the galaxy? Perhaps the answer lies in the very limit we have been discussing. Perhaps every civilization, no matter how advanced, encounters the same impassable barrier. The speed of light is not unique to human physics, it is universal. If intelligent life arises elsewhere, they too must grapple with the impossibility of faster-than-light travel. They too must face the reality that their empires, no matter how grand, will be confined to local clusters of stars, isolated islands in a cosmic ocean too vast to bridge. The Milky Way is 100,000 light-years across. Even travelling at light speed, which we cannot, crossing it would take 100,000 years. For any species, even one far more advanced than ours, building a galaxy-spanning empire may simply be impractical. Communication across such distances becomes absurd. Control becomes impossible. The speed of light does not just limit travel, it limits coherence, unity, the very possibility of galactic civilization as we imagine it. Perhaps we're not alone. Perhaps the galaxy teems with life. But perhaps every civilization is confined to its own small corner of space, forever isolated by the same cosmic speed limit, looking outward at stars they can see but never reach. The Fermi paradox may not be a paradox at all, but a direct consequence of the universe's deepest law. Still, we innovate, we dream, we push against the boundaries of what is possible. Antimatter propulsion offers theoretical promise. When matter and antimatter meet, they annihilate completely, converting mass directly into energy with perfect efficiency. No chemical reaction, no fusion process can match this power. With sufficient antimatter fuel, spacecraft could theoretically achieve significant fractions of light speed, perhaps even approaching the percentages where time dilation becomes meaningful. But the challenges are staggering. Antimatter is the rarest, most expensive substance in existence. Producing even a single gram requires more energy than entire nations consume. Storing it safely, containing it without contact with normal matter, developing engines that can harness its power. These are problems that may take centuries to solve, if they can be solved at all. Fusion propulsion, harnessing the same process that powers stars, offers a more accessible path. Fusion drives could achieve velocities far beyond anything chemical rockets can manage, perhaps reaching 10 or 15% of light speed. Projects like Project Daedalus, conceptualized decades ago, showed that fusion-based interstellar travel is theoretically feasible with sufficient investment and development. Yet even fusion runs into the same fundamental wall. 10% of light speed is extraordinary by human standards. It would revolutionize interstellar exploration, but it is still only 10%. A journey to even the nearest stars would still span decades. The universe remains vast and our tools remain limited, and perhaps that is not a tragedy. Perhaps it is an invitation. Limitations do not destroy creativity. They focus it. They force us to become more clever, more resourceful, more imaginative. Knowing we cannot travel faster than light, we develop technologies like quantum entanglement communication, exploring whether information itself might move in ways matter cannot. We investigate wormholes not to build them, but to understand the deeper geometry of space-time. We search for loopholes not in arrogance, but in wonder. The beauty of a speed limit is that it defines the game. It tells us the rules. And once we know the rules, we can play optimally. We can strategize. We can maximize what is possible within the boundaries we're given. Humanity's future among the stars may not look like Star Trek. It may be slower, quieter, more patient. It may involve journeys measured in generations, civilizations that exist solely in transit, colonies separated by centuries of communication lag, forever independent, forever alone, yet part of a species that spans multiple worlds. This is not defeat. This is adaptation. This is humanity doing what it has always done, accepting reality and then transcending it not by breaking the rules, but by mastering them. The speed of light is a limit, yes, but it is not a prison. It is the framework within which our story will unfold, and that story, constrained though it may be, remains the greatest adventure our species will ever undertake. We cannot outrun light, but we can learn to dance with it, to move within its rhythms, to explore the cosmos not by conquering it, but by understanding it. We have journeyed through the mathematics of impossibility, traced the contours of relativity, and stood at the threshold of barriers that cannot be crossed. 3 walls rise before us, each absolute, each unyielding. The need for infinite energy to accelerate mass to light speed. The dissolution of time itself as simultaneity collapses into paradox. And the violation of causality, the fundamental order that prevents effect from preceding cause. These are not engineering challenges waiting for better technology. They are the architecture of reality itself, woven into the fabric of space-time by laws that predate stars, planets, and life. The dark reality settles upon us like the vast silence between galaxies. We are, in all likelihood, forever confined to our local stellar neighborhood. The distances between stars are not merely vast, they are cosmically insurmountable. Alpha Centauri, our nearest stellar neighbor, lies over 4 light-years away. At 10% of light speed, an achievement that would require unimaginable energy and technological mastery, the journey would still take over 40 years. The far reaches of our galaxy, those spiral arms glowing with billions of stars, may remain eternally beyond our grasp. We are islanders in an ocean so wide that even light itself requires millennia to cross it. Yet within this darkness there is light, not the light of defiance, but the light of understanding. These cosmic speed limits are not prison walls, they are revelations. They tell us that the universe operates according to principles more elegant and profound than we could have imagined. The impossibility of light speed travel is not a cosmic cruelty. It is a signpost pointing toward deeper truths about existence, causality, and the nature of time itself. Einstein did not discover limitations. He discovered the grammar of the universe, the syntax by which reality speaks. To understand why we cannot travel at light speed is to comprehend our place in a cosmos governed not by chance, but by absolute physical laws. These laws apply equally to every particle, every photon, every galaxy spinning in the void. We are not excluded from cosmic wonders. We are participants in them, bound by the same rules that guide the motion of distant quasars and the decay of subatomic particles. In this uniformity there is beauty. In this constraint there is meaning. Perhaps the journey of understanding why we cannot reach light speed is more valuable than the destination itself. The mathematics that reveal these barriers also illuminate the mechanisms of stars, the expansion of the universe, and the very flow of time. They allow us to peer backward to the first moments after the Big Bang, and forward to the heat death of all things. The speed of light is not a barrier that blocks our view. It is a lens through which we see reality more clearly. Before we drift into the silence of contemplation, I invite you to become part of this journey. If this exploration has sparked wonder in your mind, please like this video, subscribe to our channel for more journeys through the cosmos and the mysteries of science. And in the comments below, share with us where you're watching from, what corner of Earth you call home, as we all look outward together toward the same unreachable stars. We close with this thought: some destinations are not meant to be reached, they are meant to be understood, and in that understanding we discover not limitation, but liberation. The universe has set a speed limit not to confine us, but to protect the very structure of reality itself. In accepting this truth, we do not surrender our dreams, we transform them into something deeper, knowledge that transcends distance and endures beyond time.